And also, we look at 1, 2, 3, 4 examples to say, well, how we use this to so-called recognize or accept a strings, eventually the language. Okay. Okay, so the formal definition. So, okay. So a PDA, let's say L, is a 6-tuple. Well, we have a few more items. Q, sigma, gamma, delta, Q0, F. You see that this is the gamma here, right? Is the stack symbols. Okay, so where? Say Q, sigma, Q0, and F, they are defined as for F8, right? So generally it's non-deterministic. Okay. All right. So Q is a finite set of states that includes Q0. Q0 is an initial or start state, and sigma is the input alphabet, and F is a set of accepting state that we use it to determine acceptance or rejection. Well, what about gamma? Gamma is, we call the stack alphabet, right? So this is a stack alphabet. So it is non-empty finite set of symbols because it's an alphabet. As usual, the most important pieces of or components is going to be the delta function and the delta. So we call the delta as usual, one-step non-deterministic transition function. Okay, but this time is a little bit more complicated than the NFAs. The domain is that we have to identify 3 things, right? Well, you give me the current state, and you give me the symbol that you are scanning that includes epsilon, so sigma union epsilon, and then we have to know the top stack symbol. So you give me the top stack symbol, or you ignore, right? So this. So you can see that this domain captures these 3 combinations, these three possible combinations. Current state, symbol being scanned, including epsilon. Top stack being sent or scanned, including epsilon. And the codomain is, because it's not deterministic, so that means we allow multiple or possible transitions from the same combination. However, the first is always we do an update, and then we advance if needed. Otherwise, we are going to stay put. So we don't have this component because it's become automatic. We either advance the read head or we stay. But as I said, the top stack may be replaced by generally another symbol or epsilon. So the outcome is going to be gamma union this possibility. However, this will only give us one choice, right? Because this is one combination. We really want to say we could have multiple such possibility. So as usual, the trick is, then this is going to be the power set, right? So remember this notation, this is the power set, or this Q cross this. So in other words, that allows us to say, well, one possibility is one updated state together with the stack symbol we're going to use to replace the top stack. And then another possibility is possibly another state together with the top stack that's used to replace the old top stack, and so on. And we are not worried that this will be infinite possibility, because it can't. You can see that the choices here will be the combination of this, which is finite, and also the combination of the top stack. Well, how the top stack symbol is finite because it's an alphabet. So there's not a lot of these. Together you could have only a finite number of possibilities. So this we are not worried that it's going to be infinite choices. Okay, so that's the formal definition. And then, as before, we want to describe the computation and acceptance, and then language acceptance, and then we look at example. Okay. So, as usual, one-step computation. Right, one step. So the one-step computation is to interpret this delta function, right? So maybe say we have Q in Q, and then A in sigma or free lunch, and a top step is in gamma or ignore. So we say, oh, delta Q A A. Maybe you have a few choices generally, and it could be empty, right? This could be empty. So one is P1, and then we have this say B1 or P2 and B2, another combination, and so on. So this is PK, Pn, say Bn. So actually, the idea is that from this configuration, say QA, you can draw this picture like we can say Q, and then sensing A, right? And then the top stack is A, right? And then it's bound to all this possibility. So generally, this is a computation tree, right? It's not always linear, like deterministic. So this configuration is we move to P1, right? And then depending on what we have, right? So this configuration, and then we replace the B with, replace the A with the B1. So what will be this symbol? Well, depending on what we have here, right? Okay. So and then we may another possibility. We may go to state P2 and then replace A by P1 and so on. So this will be sort of the possibility. Now this could be empty, right? So this could be empty, just like the NFA. If it is empty, then we hang the machine. That means no way out at that moment, from that point onward. But it may be just one of the possible branches, right? So it doesn't mean that the entire computation stops. It just means that that particular branch that you are considering, and you run into a dead end. But other branches may survive. Other branches may still be alive, right? So generally, if you start from Q0, say A, and then the top stack initially is empty, right? So you may see that this is a computation tree, right? So this is sort of the initial configuration, right? So you start with the Q0 start state, right? And then A is the very first symbol being scanned. So we are like this, Q0, and then sensing, and this is A, really the very first symbol. Well, it may be empty, okay? So depending on the programmer intent, and is there anything in the stack? Nothing at the moment. So this is really empty at the moment, okay? So this is the initial, so this is the starting configuration, right? Okay, or initial configuration. And then it moves. So from this point onward, you may come up with, say, 4 branches. And then 1 branch here, 2 branches here, 3 branches here, and then this one stop, nothing, right? It comes to a dead end like this, right? So this branch closed. But then other branch continues because it's not a deterministic machine. So in the end, but like I draw, so it's like going to be like this. Some may go forever. That's pretty bad, right? We just don't know when it's going to end. May not end, maybe in a loop, circling around. But just like what we're going to define, if we get lucky, and somehow all this configuration stop and stop in a good state in F, then we are set. Okay, so we define that. Okay, so so let me erase the middle part. This informal description. Okay, so the multi-step computation or acceptance is a concatenation of these one steps, right? So a multi-step scenario is a concatenate, so multiple one steps computation. Okay, so the result is like a computation tree, right? So generally, so it's a computation tree, right? Not a path. And some branches may be closed prematurely. Okay, so based on this, so if we have a string, okay, say x in sigma star, so what will be the acceptance, right? When we say, well, we're going to accept this, okay? The definition is similar to acceptance of NFAs, okay? But the NFA doesn't really care about the stacks, but we have a stack, okay? So here, for PDA, right? So we also with the use of a stack, right? So we have to take that into the consideration. But nonetheless, it is rather intuitive. The stack is helping, okay? But the decision is really based on the ultimate state that we are in. So these two things still valid. One is decision made when entire input, right? Entire input is complete, is processed. Not just partially, the entire, right? So all of them. And remember, we do not know how many symbols are coming, so there's no idea we could say, yeah, we know this is the end. Generally, we do not know that, okay? So a lot of time you make guess, and you hope that your kid brother, you guess your kid brother correctly, and your kid brother stop and no input, all right? So the first is that you have to, the decision maker, and then when the input is the entire input has been processed, right? Then it all depending on the ending state, right? Okay, and we use this whether you are in F or not in F to make the correct decision, whether you accept or you reject. Okay, so these two ideas still hold, or these two requirements still hold, but we have a step that we have to deal with. So what do we mean by a string is accepted? So x in sigma star is accepted, say, by this PDA M that we state, if and only if we do not know how this happened, but we just assume that, yes, there we are lucky. We are lucky that there is a computation path, right? So let me use a different color. So we are lucky that from this initial configuration, we have a computation path that eventually we get to this, right? One of them, at least one of them, that this state, okay, is in F. And at the same time, we finish processing the entire input. So entire input is processed. When we get to the bottom of it, some of them, we may still circling around. We are partially somewhere in the input because we may use epsilon transition, epsilon transition, epsilon transition. So we don't really advance the read hand. But here we may use epsilon transition, but then at the same time we consume the symbol. So eventually we consume all the symbol, and then we are lucky that we halt and then stop in a state and oh yeah, this is accepted. One of them. So how do we state that with notation similar to NFA? So if and only if we say that there exists a sequence of exists like or if and only if we can write x equal to say a1, a2, an for some we do not know how. We just want to be lucky that we can write x as sequence of symbols or epsilon. So ai is sigma or free lunch. So for I equal to 1, 2, n. Right? And of course, as usual, when we say n is this natural numbers, but n could be 0. So as usual is that this is epsilon when n is equal to 0. Otherwise, basically, you can write x in any way you want, as long as eventually x is going to be, the composition of this will be n, and will be x. So there are many possibilities, right? So for example, x is equal to BCAA. But you can see that x can be written as epsilon, epsilon B, epsilon CAA. Or x can be written as BC, epsilon, 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 A, epsilon, epsilon, A, epsilon, epsilon. So, infinitely many ways to view this. But one of them, we don't know which one, but just one of them somewhere, we force ourselves to say, see, if you view x as this, like one of the possibility, and you get lucky, and you follow this through, and then you get accepted. So we're going to use some notation to document this, right? So what do we mean by this computation? So basically, we want to say if we can write x in this way, and okay. So the idea is that x is this, and then we view this as a1, a2, a3, say an, right? So we want to say that there exists a sequence. So exists a sequence, let's say P0, P1, P2, P3, say all the way to say P sub n. And this takes care of the possibility of the possible sequence and also the possibility of the stack sequence. So this is S0, S1, S2, S3, Sn. So that means there exists sequence of states, say P0, P1, P2, say Pn, and sequence of strings in gamma star. This is for the stacks. So basically, this is the stack context. Okay? So S0, S1, S2, Sn. But then there must be some one-step computation that we want to enforce, such that this is initial. Right? So this must be initial. So that means P0 better be equal to Q0. And the stack initially is empty. Right? So this is the start state. And initially is empty stack. Okay? There's nothing in the stack. But generally, if we are here, right, we were in Pi minus 1 and the stack the step contents was at Si minus 1. And then we consume Ai, whether it is in symbol or free lunch, but we move ourselves to Pi, and then the step contents change to Si. So we want to describe this action, right, according to the one-step computation. So, and what we want to say is that we must have, well, this state is changed to this state. Well, but what do we mean by the stack contents change to this stack contents? It must be like this. Here, the Si, so assuming that this is Si minus 1, so this is the top stack. It is A, right? So this part here is underneath that is alpha, So alpha is in gamma star. This stack is in gamma or empty, right? It goes like this. And then change, just like that picture, change to this stack contents Si. This A is replaced by B, and B is stack symbol or nothing. And the bottom here remain the same. Right? You can only allow to touch the top stack, but not underneath that. So the only way is the delta function change this from A to B and update the state and advance the read head. So that means we want to describe this, right? So that means we must be seeing a picture like this, right? Si minus 1 is written as like A alpha, and Si is going to be B alpha, right? And not only that, right? And the delta, this picture, Pi minus 1, consuming Ai, and the top stack is A, must include one of the possibility. What possibility? We update this to Pi, and we advance, and then we replace A by B, right? So it must be, one of this must be a possibility. So what would be A and B? For some, A is the stack symbol, B is the stack symbol, and alpha is some stack string, some content. Okay? So you can see that basically this describes a one-step possibility. So from here to here. And eventually, we got to make sure that, and finally, the Pn got to be in F. Okay? So this is to signify that we accept. Well, what happened to this stack content? We don't really care. Right? So usually computer scientists would say don't care. Okay? So in other words, we may have dirty the stack. We may have a lot of things left on the stack, but that's okay. Or the stack may be clean. Totally clean. That's fine. Okay? So this is the formal definition. Are we going to use the definition? No. But if you can write such definition out precisely, that means at least you learn your discrete mathematics well. Because you have to write, you have to use the existential statement, and then you have to write some conditions so to capture your thoughts clearly. If you cannot write something like this, so basically your discrete math or your logics that you learn is still fuzzy. Fuzzy. You kind of say, yeah, I can guess, I can kind of describe, but I cannot really use the precise words to describe to you. So that means you haven't learned, you haven't not really conquered the materials yet. So this is just a use of the language. There's no calculus, no algebra involved. Just say, well, can you say something you see precisely what you mean? Okay. So back to this. So from this point onward, we just assume that we have a machine and we can formulate sort of this computation, and then we can define acceptance, right? So we define a string acceptance here. We erase. So what is the language? Right, the language accepted by, say, the PDA L. So we still use the L dot. So L of M is the set of all x in sigma star, and we want to say M accepts x in the usual way, right? That definition. Okay. So so that is the definition, formal definition. So what we want to learn next is through a few examples to have some insight on the construction. Okay, so again, certainly I want to tell you some of the heuristics, like the general practice for machine construction, PDA construction. All right, so remember, whatever we said about finite state machine is still valid here. Okay, so if you recall, yesterday I said that, many days ago I said that. So the idea that in F8 is a state, right? So the state is to capture, say if you are in state Q, you want to say this picture. So whatever consume input you have. So you have all these x, right, consume input. And if you start the machine from Q0 and you draw the machine in Q, right, at the end of this, right, all this, that means the state Q must have some important characteristics. You don't just randomly to say, well, I like this state, I come here. The reason why you write your program to use that particular variable to say, I will get into this state Q. You better have a contract in your own head, in your own mind to say, well, that means this x I am seeing typically must be this. So for simple example, we say, oh, the state is even number of b's and odd number of 0, not number of a's, right? This is the agreement and contract. So any such consume input that satisfy this requirement, you should make the machine go to this state Q, because that's what you claim this state wants, right? So that kind of programming practice is still valid. That's not going to change that. Okay, so in F8, the state is that you collect all this consume input, right? On consume input, say this drive M from Q0 to this state Q. If and only if this consume input typically is like characterized by what you want to say, right? So maybe it's modulo 3 equal to 1. Maybe it has a pattern, a prefix of a pattern. So that concept still valid. Okay. The use of the state, right? But for PDA, what will be the additional, right? The heuristic is this. So for PDAs, non-deterministic, right? Okay. First is that the state, the use of state is still valid. Okay. So it's similar to the F8s, right? First. Not only that, okay, not only that, for PDA purposes, a lot of time, we use state basically to implement loops. Okay? You will see example. In programming, we like to say, keep doing this, keep doing this, keep doing this, keep doing this, until you think you see something differently. Same thing here in PDA. You will say, well, do this again and again and again. Do similar things repeatedly until you run into an input, or until you say, well, maybe I'm tired now, getting to make guesses. So you will see the use of states to implement loops extensively. Okay, so this is basically, this is what importance. And